Today we are going to discuss an important topic of inorganic chemistry, that is atomic structure. Starting from the classical theories, Dalton in 1808 proposed that matter was made up of extremely small, indivisible particles called atoms. In Greek, atomio means uncuttable. This concept continued to hold ground for a number of years. But the discovery of subatomic particles like electron, protons and neutrons led to a revision of this theory because the explanation for stability of atom was an important concern. Electron is the fundamental particle which carries 1 unit negative charge and has a mass nearly equal to 1/1837 of that of hydrogen atom. Proton is the fundamental particle which carries 1 unit positive charge and has a mass nearly equal to that of hydrogen atom. Neutron is the fundamental particle which carries no charge and has a mass nearly equal to that of hydrogen atom or proton. Thomson further in 1904 gave the plum pudding model. This model considered negatively charged electrons embedded in a sphere of positive charge, just like plum pieces are present in a pudding. This could explain the neutrality of the atom, but no other feature of the atom could be explained by this model. Moving further, Rutherford conducted scattering experiments in which a beam of alpha particles was struck upon a thin gold foil, and he observed that most of the alpha particles passed through it. Very few got deflected, but a very small number of particles, alpha particles, got back deflected. This explained the Rutherford model, in which he concluded that the atom consists of two parts. Number one is the nucleus, which is very small in size, carries positive charge, and in which the entire mass is concentrated. Protons and neutrons are present in the nucleus. The second part is the extranuclear part, which is the space around the nucleus in which the electrons were distributed. He suggested that electrons were not stationary but were revolving around the nucleus in circular orbits. Rutherford found it necessary to postulate rapid rotation of the electrons about the nucleus, just as planets go around the sun. So the electrons were also called as planetary electrons. But this model also had its own share of drawbacks. According to Maxwell's electromagnetic theory, whenever a charged particle is revolving in a field of force like that of nucleus, it loses energy continuously in the form of electromagnetic radiations. This is because when a particle is revolving, it undergoes acceleration due to change in the direction, even if the speed remains constant. Thus, the orbit of revolving electron will keep on becoming smaller, following a spiral path. In other words, the atom should collapse. But this does not happen, and the atom is stable. Thus, this Rutherford model could not explain the stability of the atom. Also, no explanation about the distribution of electrons around the nucleus was given by this model. Then, Bohr in 1913 gave the Bohr's model. The main postulate of Bohr's model are: an atom consists of a small, heavy, positively charged nucleus at the center, and the electrons revolve around the nucleus in circular orbits. Now, although an infinite number of circular orbits are possible, yet an electron can revolve only in certain permissible circular orbits, which are called energy levels or stationary states. The different energy levels are labeled as K, L, M, N depending on the values 1, 2, 3, 4 and so on. Permissible orbits are those for which the angular momentum of the electrons is an integral multiple of h upon 2 pi units. If m is the mass of the electron, v is the velocity of electron, r is the radius of the orbit and n is the integer, then mvr, which stands for the angular momentum of the electron, is equal to n h upon 2 pi. Here h is the Planck's constant. Now each energy level is associated with a definite amount of energy. The electron does not radiate energy when it is present in an allowed orbit. Such energy state is known as the ground state. Each orbit is also known as a stationary state. Here the electrons are revolving but energy of the orbit remains the same. Bohr calculated the radius of different orbits in the hydrogen atom. He gave the formula R is equal to n square h square epsilon 0 upon z pi me square. Putting the values of the constant for the first orbit of hydrogen atom, the value of R comes out to be 0.0529 nanometers, and energy of the electron in any orbit was also given by the formula shown on the screen here. Here R is the radius of the orbit or shell, E is the energy of electron in the orbit or shell, m is the mass of the electron, E is the electronic charge, and once again h is the Planck's constant. Energy for the first orbit of hydrogen atom is given by minus 13.6 electron volt per atom. Now here there is one thing very important to note, that there is a negative sign attached to the energy of electron. When an electron is at a distance infinity from the nucleus, there is no force of attraction on the electron by the nucleus. Hence, the energy of the electron at distance infinity from the nucleus is taken as 0. Now, as the electron moves towards the nucleus, it experiences a force of attraction by the nucleus. As a result, some energy is given out, and since its value was already 0, hence now it becomes negative. Now, as the electron comes more and more close to the nucleus, the attraction increases and more energy is released. Hence, the energy of the electron becomes less and less. This explains why the energy decreases as we move from outer to the inner levels. Next point which Bohr model explained was the quantization of electronic energy. Electrons in an atom can have only certain definite values of energy for which he gave the formula. So we say that the energy of an electron is quantized. When energy is supplied to an atom, an electron in atom may get excited or jump from ground state to higher energy level by absorbing definite amount of energy. The excited electron, being unstable, jumps back to the lower energy level by emitting energy in the form of light of suitable energy. If E1 and E2 are the energies of the lower energy level and higher energy level respectively, delta E is the difference in the energies of two energy levels, and nu is the frequency of light emitted. Here in this diagram we are using the symbol F. Then delta E is equal to E2 minus E1, which is equal to h nu. Since each energy level is associated with a certain definite amount of energy, therefore energy is always emitted or absorbed in certain discrete quantities called quanta or photons. This means that energy of the electron cannot change gradually and continuously, but it changes abruptly as the electron jumps from one energy level to another. This shows that the electronic energy by Bohr's theory is quantized. Another important aspect which Bohr model explained was the line spectra of hydrogen. According to Bohr's theory, an electron neither emits nor absorbs energy as long as it stays in a particular orbit. When an atom is subjected to high temperature, an electron in the atom may jump from the ground state to some higher energy level or excited state. Now, since the lifetime of electron in excited state is short, it returns to some lower energy level or to the ground state in one or more jumps. Each jump involves emission of energy in the form of photon of light of definite frequency. As we read earlier, delta E is equal to E2 minus E1, it is equal to h nu. The new frequency can be given by C upon lambda. So, putting the values, we get delta E is equal to hc upon lambda. From here, we can calculate the wavelength lambda, which is equal to hc upon E2 minus E1. Corresponding to the frequency or wavelength of each photon emitted, there appears a line in the spectrum. Thus, it explains the line spectrum of hydrogen and hydrogen-like particles. But we observe large number of lines in the spectrum of hydrogen. Any given sample of hydrogen contains an almost infinite number of atoms. Under normal conditions, the electrons of each hydrogen atom remains in the ground state near the nucleus, which is n is equal to 1, or we can say which is the K shell. When a specific heat or electrical energy is supplied to hydrogen gas, it absorbs different amounts of energy to give absorption spectra of hydrogen. Some of the atoms absorb energy to shift their electron to the third energy level, while some other may absorb a large amount of energy to shift their electron to the fourth, fifth, sixth or seventh energy levels to give different types of hydrogen absorption spectrum diagram. The electrons of hydrogen in the excited state are relatively unstable and hence drop back to the ground state by the emission of energy in the form of spectrum. Therefore, different drop back means different lines of the hydrogen spectrum. Series of the spectrum lines for the hydrogen atom are named according to the names of their discoverer: Lyman, Balmer, Paschen, Brackett and Pfund. This emission spectrum lies from the ultraviolet region to the far IR region. Spectral lines we observed have been grouped into 5 series as told earlier. Number 1 is the Lyman series. These include the lines emitted by transition of electron from an outer orbit to the first orbit of quantum number n is equal to 1, and this series lies in the UV region. Balmer series, the only series which lies in the visible region. It includes the lines emitted by transitions of the electron from an outer orbit of quantum number n greater than 2 to the orbit of quantum number n is equal to 2. Paschen series includes the lines emitted by transition of the electron from an outer orbit to the orbit of quantum number n is equal to 3, and it lies in the near IR region. Bracket series includes the lines emitted by transition of the electron from an outer orbit of quantum number n more than 4 to the orbit of quantum number n is equal to 4, and this series lies in the far IR region. Another series which also lies in the far IR region is the Pfund series, which includes the lines emitted by transition of the electron from an outer orbit of quantum number more than 5 to the orbit of quantum number n is equal to 5. Here we can see the Lyman series, Balmer series, Paschen series, Bracket series and the Pfund series. Balmer series is the only series which lies in the visible region. The wavelength of the emitted spectral line when an electron of hydrogen atom jumps from higher orbit n2 to lower orbit n1 is given by the Rydberg's formula 1 upon lambda is equal to RH 1 upon n1 square minus 1 upon n2 square, where RH is the Rydberg constant and for hydrogen spectrum its value is equal to 109,737 centimeter inverse. N1 is defined as the lower level and so is less than the value of N2. From here we can calculate the value of the wavelength or the wave number of the emitted spectral line. The usefulness of Bohr's model was that it could explain the stability of the atom. It explained the line spectrum of the hydrogen which we just studied and also explained the quantization of electronic energy. But Bohr's model also had its own share of limitations. It could explain the spectra of hydrogen, but it failed to explain the intensities of the spectral lines. Its inability to explain the line spectra of multi-electron atoms. Inability to explain the Zeeman effect, which is the splitting of lines in the magnetic field. Also, it could not explain the splitting of lines in the electric field, that is the Stark effect. Bohr's model was also not in accordance with the Heisenberg's uncertainty principle and also the de Broglie concept of dual character of matter, which we will also study in this topic today. To overcome the shortcomings of Bohr's model, new models were proposed on the basis of two new concepts, de Broglie concept and Heisenberg's uncertainty principle. The new model is known as the quantum or wave mechanical model. Let us first study about the de Broglie concept. In 1924, de Broglie reasoned that similar to the dual behavior of radiation, material particles like electrons also should behave both as particle as well as wave. Thus, every particle is associated with a wave whose wavelength lambda is given by the equation lambda is equal to h upon p, where h is the Planck's constant and p is the momentum of the particle. For a particle of mass m and velocity v, momentum p can be expressed as p is equal to mv, and when we put the value of p in the previous equation, we get lambda is equal to h upon mv. According to de Broglie, the electron is not merely a particle but has also got wave-like character. For the electron wave to move in a circular orbit continuously, the wave motion must be in phase, which means that starting from a given point as shown in the diagram here, the two ends of the wave must meet at the same point. If not so, that is, if the two ends of the wave do not meet, the wave motion is said to be out of phase. This now means that for wave motion to be in phase, the circumference of the circular orbit must be integral multiple of the wavelength lambda. That is, the circumference 2 pi r is equal to n lambda, where n is an integer 1, 2, 3. Using the de Broglie concept, lambda is equal to h upon mv. So putting the values, 2 pi r is equal to n h upon mv. From here, it is concluded that mvr is equal to nh upon 2 pi. Since mvr is the angular momentum, it can be concluded that only those circular orbits are permitted for which the angular momentum is an integral multiple of h upon 2 pi units. This is the same idea which Bohr postulated earlier but was explained by de Broglie concept. Let us take an example. There is a cricket ball of mass 6 into 10 to the power minus 2 kg, which is moving with a speed of 62 meter per second, and we have to calculate the wavelength associated with this moving ball. Putting all the values, we get lambda in the range of 10 to the power minus 34 meter, which shows that it is too small to be observed. So de Broglie concept holds good for microscopic articles or the particles, but not for macroscopic particles. Since we come across macroscopic objects in our everyday life, so it has no significance and we do not observe wave nature associated with the motion of a running car or a ball, etc. Next concept is the Heisenberg's uncertainty principle. According to this, it is impossible to measure simultaneously both the position and momentum of microscopic particle with absolute accuracy or certainty. The mathematical relationship given here is delta x into delta p is greater than equal to h upon 4 pi. Delta x stands for the uncertainty in position and delta p stands for the uncertainty in momentum. In this principle, the important word which is or the term which is to be noted is measure simultaneously, which means that delta x is inversely proportional to delta p and vice versa. In other words, if delta x is small, that is, there is very little uncertainty in the position of the particle, then delta p would be large, that is, there would be large uncertainty regarding momentum. Similarly, if delta p is small, that is, very little uncertainty in the momentum of the particle, then delta x would be large, that is, there would be large uncertainty regarding the position. So it can be concluding, if exact momentum is to be measured, then the exact position will not be exactly known and vice versa. So now again, this was the mathematical equation for Heisenberg's uncertainty principle. Delta x into delta p is greater than equal to h upon 4 pi. Momentum p, as we have already read, is equal to mv. So delta p will be equal to delta mv, but m being constant, that means the mass being constant for any particle, delta p is equal to m delta v. Putting these values, we get delta x into delta v is greater than equal to h upon 4 pi m. Hence, maximum uncertainty in velocity can also be calculated. Knowing the radius of the atomic nucleus, which is of the range 10 to the power minus 14 meter, and putting all other values for electrons, delta V is calculated, and here we find that the uncertainty in the velocity of electron is much higher even than the velocity of light. So it is not possible. That is why we can conclude that electron cannot exist in the nucleus. We observe that finding of precise position and path of an electron is not possible. So we can only think in terms of the probability of finding an electron at a particular position rather than specific position, and that we will study in the wave mechanical model of the atom. The uncertainty principle is not considered for simultaneous measurement of the position and momentum of large objects in daily life. This is because the size of such objects is very large as compared to the wavelength of light used, and also their momentum is very large as compared to the momentum of photons of light used. As a result, their uncertainty involved will be insignificant, which can be overlooked. Again, we take an example. We have a golf ball which has a mass of 40 gram and a speed of 45 meter per second. If the speed is measured with an accuracy of 2%, and we have to calculate the uncertainty in position. Uncertainty in speed can be calculated as 2% of 45, which comes out to be 0.9 meter per second, and when we put these values, then we get the answer in the range of 10 to the power minus 33 meters, which is an insignificant value. So, we say that the uncertainty involved will be insignificant, and this can be overlooked. Thank you.